In this lecture, I am going to present the analysis of portal frame by stiffness matrix method by solving one problem. So first, coming to the step-by-step procedure used for the analysis of portal frame by stiffness matrix method. So these are the different steps. First, determine the degree of kinematic indeterminacy, that is degree of freedom. Then identify the independent displacement components. Then assign the coordinate directions to the independent displacement components. Then prevent all the independent displacement components to obtain the restrained structure. Then determine the forces required at the coordinates in the restrained structure due to the loads other than those acting at the coordinates. Then determine the stiffness matrix by giving unit displacement to the restrained structure in each of the coordinate direction and find the forces developed in all the coordinates. Then compute the final forces in the coordinate directions. Then by using the stiffness equation, P is equal to P dash plus P delta, then P is equal to P dash plus K into delta, where K is the stiffness matrix and delta is the displacement matrix and P is the force matrix. Then by using the condition of equilibrium of forces to compute the displacements in the coordinate directions. Delta is equal to K inverse P minus P dash. Then after knowing the displacements, compute the internal member forces by using the slope reflection method. These are the step-by-step procedures to follow for the analysis of the portal frame. Then coming to the problem, using the stiffness matrix method, analyze the frame shown in figure, take EI is constant throughout. So this is the portal frame, A, B, C, D, E. The vertical member AB and CD length is 6 meter and the horizontal member BC length is 6 meter and C length is 4.5 meter. The support A is fixed and D is fixed and the support E is hinged. And on the span BC, there is having a uniform distributed load of intensity 40 kN by meter throughout the length. So in this method, first you have to find out the degree of kinematic indeterminacy or degree of freedom. So you know what is the degree of kinematic indeterminacy formula. So dk is equal to 3j minus r plus m, where j is the joints and r is the number of reaction component and m is the number of members. So in this problem, the number of joints j is equal to 1, 2, 3, 4, 5. Joint is 5. Then the number of reaction component, that is equal to, at support A 3 reaction components, at support D 3 reaction components and at support E 2 reaction components. So the total reaction is 3 plus 3 plus 2. So the reaction component is equal to 8. Then the number of members, that is equal to 4. AB, BC, CD and C. So the number of members are equal to 4. M is equal to 4. Then find out the degree of kinematic indeterminacy. So this is equal to 3 into 5 minus 8 plus 4. The degree of kinematic indeterminacy is equal to 3 into 5 minus 8 plus 4. So this is equal to 3. So the degree of kinematic indeterminacy or the degree of freedom is equal to 3. So in this problem, choose 3 unknown displacement components. At A there is no displacement takes place, at D there is no displacement takes place, but at B the rotational displacement takes place, and at C the rotational displacement takes place, and at D the rotational displacement takes place. So in this problem, choose the unknown displacements are the rotation at B, C and E. Hence the coordinates selected at B, C and E. Assign 3 coordinates. One is at B, second one is C and the third one is at E. So assign 3 coordinates at B, C and E respectively. So this is the coordinate direction at B, C and E. So this is the first coordinate at B, this is second coordinate at C, and this is third coordinate at E. So this is the forces required at the coordinates in the restraint structure due to load. So first determine the forces required at the coordinate in the restraint structure due to load. So prevent all the independent displacement components to obtain the restraint structure as shown in figure 2. In this problem, first find out the forces required at the coordinates in the restraint structure due to load. So prevent all the independent displacement components and obtain the restraint structure. So first step to take all the supports are fixed. There is no displacement takes place. Then find out what are the fixed end moments at the end of the member. Then after getting the fixed end moments, then find out what are the forces which is acting in the coordinate direction 1, 2 and 3 respectively. So this is the fully restrained structure and these are the coordinates. So first find out what are the fixed end moments due to the external loading. On the span BC, there is having the 40 kilonewton by meter load UTL. This is on the span BC, there is having the 40 kilonewton by meter uniform distributed load throughout the span. So due to this load, first find out what is the moment at this end and what is the moment at this end. So find out MFBC and MFCB. But at other span, there is no loading. So the fixed end moment MFAB is 0, MFB is 0, then MFC is 0, MFEC 0, then MFCD 0 and MFDC 0. The fixed end moments of the other span, that is 0. Only find out the fixed end moment of the span BC, MFBC and MFCB. So find out the fixed end moment due to the UTL on the span BC. So MFBC is equal to minus 40 into 6 square by 12 and MFCB is equal to plus 40 into 6 square by 12. So this is the fixed end moments. MFBC is equal to minus 40 into 6 square by 12. So this is equal to minus 120 kilonewton meter and MFCB is equal to plus 40 into 6 square by 12 plus 120 kilonewton meter. Then other fixed end moments MFAB, MFBA, MFCD, MFDC, MFC, MFEC all are 0. As in other spans, there are no loading. So the fixed end moments MFAB is equal to MFBA is equal to 0 and MFCD is equal to MFDC is equal to 0. Then MFC is equal to MFEC is equal to 0. Then find out the forces developed in the coordinate directions due to given loads. So here find out what is the force in the coordinate direction 1, 2 and 3. Here you got MFBC and MFCB. So MFBC is equal to P1 dash and P2 dash is equal to MFCB plus MFC, but MFC is equal to 0 as there is no load on the span C. So MFC is equal to 0 and MFCB is equal to plus 120 kilonewton meter. So P2 dash is equal to MFCB plus MFC and P3 dash is equal to MFEC. Here MFEC is also equal to 0. So find out the forces P1 dash MFBC is equal to minus 120 kilonewton meter and P2 dash MFCB plus MFC plus 120 kilonewton meter. So this is the force due to the external loading P1 dash, P2 dash and P3 dash. So P1 dash is equal to minus 120 kilonewton meter, P2 dash is equal to 120 kilonewton meter and P3 dash is equal to 0. This is the force developed in the coordinate direction due to the external loading. Then what are the forces acting at the coordinates? So take this is the force P is equal to P1, P2, P3. So there are 3 coordinates. So at coordinate 1 the force is P1, at coordinate 2 the force is P2 and at coordinate 3 the force is P3. Here there are no forces acting in the coordinate direction. So P1 is equal to 0, P2 is equal to 0 and P3 is equal to 0. So P is equal to 0, 0, 0. So this is the column matrix. This is the external force at the coordinates. P is equal to 0, 0, 0. Then find out the stiffness matrix. So here determine the stiffness matrix by giving unit displacement to the restrained structure in each of the coordinate direction and find the forces developed in all the coordinate directions. First apply unit rotation in coordinate direction 1. So apply unit rotation. So this is the coordinate 1, this is coordinate 2, this is coordinate 3. So first apply the unit rotation in the coordinate direction 1, theta is equal to 1. And all other supports are fixed. Only on restrain this support and apply the unit rotation in coordinate direction 1. Then find out what is the force due to the unit rotation at 1. Determine the forces at coordinate 1. This is K11 and forces at coordinate 2. This is K21 and forces at coordinate 3. So this is K31. Apply 1 radian rotation to support B in coordinate direction 1. Then the forces developed in the coordinate direction 1, 2, 3 are found by using the slope deflection equations. So here you find out the force at coordinate 1 due to the unit displacement at coordinate 1, due to the unit rotation at coordinate 1. And here K11. K21 is the force at coordinate 2 due to unit rotation at coordinate 1. And K31 is the force at coordinate 3 due to unit rotation at coordinate 1. So find out K11, K21, K31. When you find out K11, so you have to find out from this span and from this span. So from this span, from the span BC, so K11 is equal to 4EI theta B by L plus 2EI theta C by L. And from this span, AB span, K11 is equal to 4EI theta B by L plus 2EI theta by L. But AB span length is given 6 meter and BC span length is given 6 meter. So put this value here. K11 is equal to 4EI theta B by 6 plus 2EI theta by 6 plus 4EI theta B by 6 plus 2EI theta C by 6. But you know the end conditions. So here theta A is equal to 0 and theta C is equal to 0 and theta B is equal to 1. So this is the end condition. Then put the end condition in this expression. So K11 is equal to 4EI theta B by 6 plus 4EI theta B by 6 is equal to 4EI theta B by 3. But you know theta B is equal to 1. So here you put the value of 1, theta B is equal to 1. So K11 is equal to 4EI by 3. Similarly find out K21 and K31. So for K21 find out only from this span CB. So K21 is equal to 4EI theta C by L plus 2EI theta B by L. K21 is 4EI theta C by 6 plus 2EI theta B by 6. But you know the end conditions. So after putting the end conditions, K21 is equal to EI theta B by 3. But you know theta B is equal to 1. So K21 is equal to EI divided by 3. Then find out K31. Due to the unit rotation at B, there is no effect on the support E. So K31 is equal to 0. K31 is equal to 0. These are the force you got at coordinate 1 and at coordinate 2 and coordinate 3 due to unit rotation at coordinate 1. Then apply unit rotation in coordinate direction 2. So you have to make the support C is on restraint and all other supports are restrained and apply the unit rotation at coordinate 2. So here you apply the unit rotation theta is equal to 1 and all other supports are restrained or fixed. And here theta B is equal to 0 and here theta E is equal to 0 and here theta D is equal to 0. And due to this unit rotation, find out what is the force at coordinate 1 and what is the force at coordinate 2 and what is the force at coordinate 3. So K12 is the force at coordinate 1 due to unit rotation at coordinate 2 and K22 is the force at coordinate 2 due to unit rotation at coordinate 2 and K32 is the force at coordinate 3 due to unit rotation at coordinate 2. So find out this K12, K22 and K32. for K12 find out from this span only, BC span. So K12 is equal to 4EI theta B by L plus 2EI theta C by L. And K22 find out from this span, and from this span. The rotation takes place in these three span. So from the span BC, K22 is equal to 4EI theta C by L plus 2EI theta B by L. And from the span CD, K22 is equal to 4EI theta C by L plus 2EI theta D by L. And from the span C, K22 is equal to 4EI theta C by L plus 2EI theta E by L. Then K32 find out only from this span. So K32 is equal to 4EI theta E by L plus 2EI theta C by L. This is K22 is equal to 2EI theta B by 6 plus 4EI theta C by 6 plus 4EI theta C by 4.5 plus 2EI theta E by 4.5 plus 2EI theta D by 6 plus 4EI theta C by 6. So this is equal to K22 is equal to 4EI theta C by 6 plus 4EI theta C by 4.5 plus 4EI theta C by 6. So this is the expression after putting the value of theta B, theta C, theta E and theta D in this expression. Then you know theta C is equal to 1. Then after putting the theta C value here, so K22 is equal to 2.222 EI. Then find out K32. K32 is equal to 4EI theta E by 4.5 plus 2EI theta C by 4.5. Then after putting the value of theta E and theta C in this expression, so K32 is equal to this one, 0.444 EI. Then apply unit rotation in coordinate direction 3. So this is the coordinate direction 3. So here you apply the unit rotation. You have to make this support is unrestrained and all other supports are restrained, and you have to apply the unit rotation at coordinate direction 3. So here you have to apply theta is equal to 1 and other supports are fixed. Theta C is equal to 0, theta B is equal to 0 and theta D is equal to 0 and theta A is equal to 0. Only theta is equal to 1 at support E. 1 radian rotation is given to support E in coordinate direction 3. Then forces developed in the coordinate direction 1, 2, 3 are found by using the slope deflection equation. So these are the end conditions: theta B 0, theta C 0 and theta E is equal to 1. So here you find out, so here K13 is the force developed at the coordinate 1 due to unit rotation at the coordinate 3. K23 is equal to force developed at the coordinate 2 due to unit rotation at the coordinate 3. And K33 is equal to force developed at the coordinate 3 due to unit rotation at coordinate 3. So find out this force K13, K23 and K33. So at the rotation takes place at E, there is no effect on the coordinate 1. So K13 is equal to 0. Then find out K23. So K23 that you can find out from this span C. So here K23 is equal to 4EI theta C by L plus 2EI theta E by L. Then K33 also find out from this span. So K33 is equal to 4EI theta E by L plus 2EI theta C by L. And the end condition theta B 0, theta D 0 and theta C 0, only theta E is equal to 1. So this is theta B 0, theta C 0, theta E is equal to 1, K13 is equal to 0, then K23 is equal to 2EI theta E by 4.5 plus 4EI theta C by 4.5. So this is equal to 2EI theta E by 4.5 because theta C is equal to 0. So K23 is equal to 0.444 EI. Then find out K33. K33 is equal to 4EI theta E by 4.5 plus 2EI theta C by 4.5. So after putting the end conditions, so the equation becomes 4EI theta E by 4.5. Then after putting theta E is equal to 1, so K33 is equal to 4EI by 4.5. So this is equal to 0.889 EI. So this is the force at coordinate 1 due to unit rotation at coordinate 3, force at coordinate 2 due to unit rotation at coordinate 3 and force at coordinate 3 due to unit rotation at coordinate 3. Then by using the stiffness equation, find out the displacements. So here this is the stiffness equation. P is equal to P dash plus K into delta. Then K delta is equal to P minus P dash. So here this is the stiffness matrix. K is the stiffness matrix. So this is K11, K12, K13, K21, K22, K23, K31, K32, K33. These are the forces at coordinate 1, coordinate 2, coordinate 3 due to unit rotation at coordinate 1. And these are the forces at coordinate 1, coordinate 2, coordinate 3 due to the unit rotation at coordinate 2. And these are the forces at coordinate 1, 2, 3 due to the unit rotation at coordinate 3. So these 9 stiffness coefficients become the stiffness matrix. And this is the displacement matrix, column matrix. And these are the external forces which is acting at the coordinate, but in this case the external force is 0, and these are the forces due to the given loading. Then put the value of stiffness coefficient in this expression. So K11, K12, K13, K21, K22, K23, K31, K32, K33. These are the values. Then this is the displacement. This is the external force, and this is the force due to the external loading. Then here this is the expression. Then here you take the delta 1, delta 2, delta 3 is equal to 9 by EI, 12, 3, 0, 3, 24, 0, 4, 8, minus 1. So this is the inverse of the stiffness matrix, and this is the force matrix, and this is the displacement matrix. Then first find out the inverse of the stiffness matrix. This is 3 into 3 matrix. This is 3 into 3 matrix, and first find out the inverse of the stiffness matrix. Then multiply with the force matrix. Then you get the displacement delta 1, delta 2, and delta 3. So delta 1 is equal to 109.565 by EI, and delta 2 is equal to minus 78.261 by EI, and delta 3 is equal to 39.130 by EI. So here delta 1 is equal to theta b is equal to 109.565 by EI, and delta 2 is equal to theta c is equal to minus 78.261 by EI, and delta 3 is equal to theta e. So this is equal to 39.130 by EI. So these are the rotations you got at B, C, D. That is at coordinate 1 and coordinate 2 and coordinate 3. Then after knowing the displacement, then you can find out the internal forces. So find out the final moments by using the slope deflection equations. So here you find out the final moment MAB, MBA, MBC, MCB, MCE, MEC, then MCD, then MDC. You know the fixed end moments at the end of each members, and you know the rotation at B, C and E, theta B, theta C and theta E. Rotation at A is 0 and rotation at D is equal to 0. So using these values, find out what is the moment at the end of each member. MAB, MBA, MBC, MCB, MCD, MCE, MEC, then MDC. The final moments MAB is equal to MFAB plus 4EI theta A by 6 plus 2EI theta B by 6. Then put the value of theta A, theta B here. Theta A is equal to 0 and theta B is equal to 109.565 by EI. Then after simplification, MAB is equal to 36.522 kilonewton meter. Then find out MBA. MBA is equal to MFBA plus 4EI theta B by 6 plus 2EI theta A by 6. So put the value of theta B and theta A. Theta B is equal to 109.565 by EI and theta A is equal to 0. Then after simplification, MBA is equal to 73.043 kilonewton meter. Then find out the MBC. MBC is equal to MFBC plus 4EI theta B by 6 plus 2EI theta C by 6. Then put the value of MFBC, theta B and theta C. MFBC is equal to minus 120 and theta B is equal to 109.565 by EI. Theta C is equal to minus 78.261 by EI. Then after simplifying, MBC is equal to minus 73.043 kilonewton meter. Then find out MCB. MCB is equal to MFCB plus 4EI theta C by 6 plus 2EI theta B by 6. then MCB is equal to 120, MFCB is equal to 120 plus 4EI by 6 into theta C is equal to minus 78.261 by EI plus 2EI by 6 into theta B is equal to 109.565 by EI. Then after simplification, MCB is equal to 104.348 kilonewton meter. Then find out MC is equal to MFC plus 4EI theta C by 4.5 plus 2EI theta E by 4.5. Then put the value of theta C, theta E and MFC. MFC is equal to 0 and theta C is equal to minus 78.261 by EI. Theta E is equal to 39.130 by EI. Then MC is equal to minus 52.174 kilonewton meter. Then find out MEC is equal to MFEC plus 4EI theta E by 4.5 plus 2EI theta C by 4.5. Then put the value of theta E and theta C here, and MFEC is 0 and theta E is equal to 39.130 by EI and theta C is equal to minus 78.261 by EI. Then after simplification, MEC is equal to 0 because you know the end is simply supported, so here also you got the moment is equal to 0 because you know at the simply supported the moment is equal to 0. MEC is equal to 0. Then find out MCD. MCD is equal to MFCD plus 4EI theta C by 6 plus 2EI theta D by 6, and you know the theta C, theta D, and put the value of theta C and theta D. Theta C is equal to minus 78.261 by EI and theta D is equal to 0 and MFCD is equal to 0. So MCD is equal to minus 52.174 kilonewton meter. Then find out MDC. MDC is equal to MFDC plus 4EI theta D by 6 plus 2EI theta C by 6. So theta C is equal to minus 78.261 by EI and theta D is equal to 0 and MFDC is equal to 0. So put all the value and find out MDC is equal to minus 26.087 kilonewton meter. So these are the summary of final moments. MAB is equal to 36.522 kilonewton meter, MBS 73.043 kilonewton meter, MBC is minus 73.043 kilonewton meter, MCB is equal to 104.348 kilonewton meter, MC is equal to minus 52.174 kilonewton meter, MEC is equal to 0, MCD is equal to minus 52.174 kilonewton meter, then MDC is equal to minus 26.087 kilonewton meter. Then give the direction of the moments. So here MAB is equal to 36.522 kilonewton meter. So here this is clockwise direction, and MBA is equal to 73.043 kilonewton meter. This is also clockwise direction, positive, and MBC is equal to minus 73.043 kilonewton meter, negative, anti-clockwise direction, 73.043 kilonewton meter. But you check here, the net moment should be 0. So here you are getting the net moment positive, negative, so this is 0. Then MCB is equal to 104.348 kilonewton meter. This is positive, so clockwise direction. Then MC is equal to minus 52.174 kilonewton meter. So this is anti-clockwise, negative, and MCD is also minus 52.174 kilonewton meter. This is also negative, anti-clockwise direction. So here also check whether you are getting the net moment is 0 or not. So here you are getting the net moment is 0. This is clockwise 104.348 kilonewton meter, and this two is anti-clockwise 52.174 and 52.174. So total is your 104.348. So the net moment is equal to 0. Then MFEC is equal to 0, simply supported. So here there is no moment, and MDC is equal to minus 26.087 kilonewton meter. This is also negative, so the direction is anti-clockwise. Give the negative moment anti-clockwise direction and positive moment clockwise direction. So these are the direction of the moments. Then draw the bending moment diagram. So here you see, so here this is clockwise, the arrow mark is inner side, 36.522 kilonewton meter. So here you take 36.522 kilonewton meter. Then here this is 73.043 kilonewton meter. So here you take 73.043 kilonewton meter. Then here 73.043 kilonewton meter. So take this is 73.043 43 kilonewton meter, and here this is 104.348 kilonewton meter. So take 104.348 kilonewton meter, and here this is 52.174 kilonewton meter. So take here 52.174 kilonewton meter, and here 52.174 kilonewton meter. So here you take 52.174 kilonewton meter, and this side, the inner side, this is 26.087 kilonewton meter. So here take inner side 26.087 kilonewton meter. Then these 2 points, join these 2 points, then join these 2 points, join these 2 points, join these 2 points. So this becomes the negative bending moment diagram, and this side the tension inside is take positive, outside take negative. On the span BC there is having the uniform distributed load. So draw the positive bending moment diagram here. So the positive bending moment diagram is equal to W L square by 8. So W is given 40 kilonewton by meter, and L is equal to 6 meter. So 40 into 6 square by 8. So this is equal to 180 kilonewton meter. So this is the positive bending moment diagram, parabolic, because the load is having on the span BC is uniform distributed load. So due to UDL, the free bending moment diagram or positive bending moment diagram is parabolic. So this is the parabolic shape, and the ordinate here is equal to 180 kilonewton meter. So this is the positive bending moment diagram. So here this portion is cancelled due to negative and positive. So this is negative, this is positive, and this is negative. And here this is negative, and this is negative, and this inner side tension is positive. Here this is negative, and the inner side tension is positive. So this is positive, 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 and all others, these are negative bending moment diagram. So this is the complete bending moment diagram of the portal frame. So here you can find out what is the maximum positive moment here. So if you know this ordinate, then you can find out this ordinate, because the total ordinate is 180 kilonewton meter. So you have to find out this ordinate, because you know this ordinate and this ordinate. So at the center you have to find out by taking the average of these two ordinate. So what is the ordinate here you can find out. Then you have to deduct from 180 kilonewton meter, then you will get what is the maximum positive moment on the span BC. So this is the complete bending moment diagram of the portal frame ABCDE. Now all are clear that how to find out the moment of the portal frame by stiffness matrix method, then how to give the direction of the moments, then how to draw the bending moment diagram.